Okay. Dale. Come on. We can start because I have a fascinating world of calculations. So we have to take all your attention, yeah? To stay alive. Yeah. So let me know when we have to finish, yeah? Yeah. So let me go with this. So I have two blocks for you, yeah? And I will try to add one more thing because yesterday I was digging a bit for the Australian standards and I found out an interesting one. My colleague sent me the standard itself, legally discussable, but he sent it to me and I can show you one interesting thing which I think is not fully correct. It was actually not correct at all. But I think you are kind of forced to do it later. So, if someone wasn't, because not everyone was on the Monday, so I can give you back again. So I'm part of the ESIPAC. I also run my own company, and the second one used to work at Eaton, GE, and design wind turbines, design switch gears, build switch gears myself with my hands in the very beginning, and so on. And in some committees in Poland, because we also have a committees there for electrical safety. So we'll start with one thing because before the lunch, and I want to actually those are the question part of trainings I typically do. So can you spot the problem? Those are, by the way, all things that I go from the site audits, and we have to collect the data. Okay, let's go. Just take it as a brainstorm. Yeah, there's no stupid things. I doubt that you point something which is really weird. Can you spot the problems that you can have here?
Yeah, there's no IP screen.
Okay, it's no covers, yeah? Let's say. I can tell you this is a bus section breaker that you have to operate, and to operate you have to open the doors. It's not visible from the outside. So that's how you operate it. If you've seen the video before on the Monday on the cables, then you can imagine the wire strap. This will not work. Once you have a short circuit, all of these things will just go all over the place. But also from Agnes' perspective, shock hazard, fun thing is, this is almost one-to-one size. Fun thing is that technically you don't have to open this to look from the side. And those are the feeders, 160 amp, 100 amps. So despite that you might think this is a safe one, you look to the right and then you see this thing. Yeah? So that's one thing. The second thing is, my problem was that I have to open the doors to see the settings of the breaker. So that's because of me, they have to open it. But then you see everything else. Do you have something like this somewhere? Have you seen? That was in Czech Republic. You enter the substation, it is like this. Every person I usually enter substation, they look like this. So they have a PPE, but they will pretty much sometimes wear the short sleeve. Why not? Yeah, it was summer. So this was pretty much on the height like this. So I could grab whatever bus I want. Even doing the photo like this, I was pretty much somewhere like 1 meter away from. This is 415 volts, by the way. So we all see the problem is shock hazard and arc flash. Yeah? They didn't know what arc flash is at that point. What procedure you write to change this light? If someone will just tell you, I go to change light in the substation, doesn't sound like a problem, yeah? And this will be treated almost like the working, because this is the worst location. Almost like live work, but technically it is, will be treated as a dangerous conditions, which you need to go over the full permit to work just because you want to change the light, or this one, for example. And imagine someone brings the aluminum ladder. This you've seen yesterday, on Monday. This is the other one that I use sometimes on the interviews for people. You see this beautiful thing? That's the old times we have. On Monday I was looking for one thing, this working distances, yeah? And you have something called minimum safe working distance in Australia, which is 50 centimeters. I can tell you that here pretty much there is a wall. There was pretty much something like 1 meter. So if you would like to really be in the shock hazard distance, you have to walk near the wall and you don't have place to escape. Things like this still exist. So one transformer, the second transformer, and then you go to read the meter. Yeah, and this is not something you can really solve easily because technically you could put some covers back, but this thing don't have covers by default. So for installations, anyone who has any installation and have to do something with it will be subject for age, the type, environment, conditions, whatever it is. It is, yeah. It's like once you have installation, it will be just subject to all of those things. There's no question asked. We have this here. I will just keep repeating this because I'm going to show you some mitigation methods, just to go roughly through it and show you some how it works, and then we go to the calculation. Yeah. So from the mitigation, as we discussed last time on Monday, you can go from top down. So that's what I do typically. I try to eliminate, reduce on the design phase or on engineering phase. And then once we go to this point, then we go to maybe PPE selection, yeah? Because the big thing behind it is that you have to allow PPE selection at all. Because the allocation that we have, where there are like 200 calories plus. And this is not an engineering or calculation error. It is 200 calories plus. That's what they have. And you cannot select PPE for something like this. Just because you think you can select PPE, you can't. So we have to go down to the point where you actually can do this. So we will look now on three things, and because this is as a hierarchy, as a process is nice. In practice, sometimes you have one engineering control thing that like the relay or something that will solve multiple problems. So it's usually like idea is nice. We work with it, not maybe all step by step like in this way, but sometimes do 2 steps at the same time. And at the end, the solutions in the market that just allow you to fix few things, but randomly sometimes here and here. Yeah? So, in order to, I will roughly go through it and I'll show you a working example. So from elimination reduction, most of the things that we do, what I do typically, we adjust the settings because that's the cheapest thing. Also hardest to do from engineering perspective. Yeah? But this is the cheapest thing in the field later. However, if you go to the medium voltage relays and changing settings, adjusting and testing and writing the report, it's maybe not that cheap. But if you have a people in-house, then technically it's the cheapest thing you can do to improve the safety. Flash optic detection, something that already David mentioned. That this can be standalone system, relays can have it. There is a discussion is it better to have a standalone system, separate system that does this, or the relay, because of the computing power of the relay itself. The arc quenching system, that's the Arctic thing, and there are actually 3 companies doing them. David said the Schneider is doing. The Schneider is not doing. They don't have anything they are buying, but Arctic is doing for Siemens and for themselves. The quenchers, the ABB doesn't have a low voltage one. There is Dane. Dane is the company that you might know from the power, the surge protection. In Europe, they have a guy that used to work with us, with Eaton, and he is doing from Meller time, and they also do quenchers themselves. And Eaton has the quenching system from last 20, 30 years. It's not new thing, technically speaking. It's not even a new idea. This idea is like 40 years old. So I can give you later how it works. Short circuit current reduction on big networks when you have current limiting reactors does not always mean the lowest short circuit, not always mean that you have a less problem. Sometimes because short circuit has an influence on the protection time. So sometimes you can go too low and then your protection will not pick up. That's the problem with the PV, that's the problem with the inverters, yeah? With the tripping. Internal classification, I think you also follow, everyone almost follows IEC standards for it. Most of the medium voltage switches will be internal arc classified, so they will be tested for the arc which will happen inside the panel, yeah? In case of switching, whatever failure, breaker, cable failures, and it should stay inside the panel. There is a trick behind it, which I think I will not explain today, but there is a trick that you always do the test 30 centimeters away from the panel. There are some cotton testers. If they don't catch the fire, it's okay. If they catch fire, it's not okay. Which at the end means that if you stay 30 centimeters from the panel or closer, and you don't wear at least 100% cotton, you might catch fire. But the panel is arc rated. So everything we need to understand how to use, yeah? The same thing exists for the low voltage, but it's just less popular. In low voltage panels, it's very typical that when you do something, you will just open it, yeah? In medium voltage, it's rarely possible to open panel when it's energized. There's a lot of locks that you can of course bypass it if you know how it works, but it's very hard to open panel when it's energized. In low voltage, it's like we will keep opening this, yeah? So it's a very rare thing because once you open the doors, your arc rating is gone pretty much. So we look on those three things later. Then there is a lot of other things related with the so adaptive settings is an interesting topic that I use for because ARMS this is maintenance mode as a solution for the low voltage breakers. I will show you this as well. ARMS is because there's a trademark, energy reduction maintenance switch, arc flash reduction maintenance switch from I think Eaton and Schneider. But also we can do the same thing on the medium voltage, but on medium voltage you have to program it yourself in the relay. And I will show you how this can work. Adaptive settings is generally like reprogramming the relay because of the configuration of the network. And sometimes you have to do it, and the relay can do it automatically. When something changes, there's a signal, and like, okay, I'll reprogram for lower settings, higher settings, because you now run 2 lines instead of 1. Current limiting fusing is just the current limiting fuse. It is just the device that we can use sometimes. Differential protection is nice to have. IS limiter is ABB thing on the medium voltage. This is very expensive, smart fuse, which works very, very fast and is limiting the current on the medium voltage systems, which is mainly used on ships because it's so expensive. As far as I remember, I think one field, this thing costs 100,000 euro, which is like pretty much no one will, and those ships you usually have 2 supplies and you have to limit it and so on. Zone selective interlock, interesting thing, which is a communication-based protection on low voltage. Nice things to have, but it requires just the new breakers or relatively fresh breakers with communication and everything else. So usually we talk about the design thing. So we look on the arms, and the rest is, I would say, risk reduction, because IP from our projects that we go on site, covers. This is the basic stupid thing that people just keep forgetting. Usually it comes from this manufacturer with some covers, if you order it properly, and then they are just keep disappearing. Because someone did some measurements, removed the cover, didn't put it back. And then you open panel and you see live bus bar. Yes, so the covers, cheapest thing. Generally the rule behind the covers and electrical safety is what you don't see doesn't exist. That's very simple, yeah? If you don't see something, it doesn't exist. And that's how you can think about it. Because there is a plexi. Plexi is not the arc-rated topic, yeah? But it's treated as a cover. Separation form, that's what you see on the previous photo, that separation forms are just the way how you design. Physically, you have to design switchgear. You have to order 4B, 3A, 2A separation form, which means that, for example, cable connection is separated from the breaker. So that was this discussion on Monday that we have with 1 door, 3 doors, and so on. Typically, when you see 3 doors breaker, switchgear, it's 3A, 4B separation. That you have everything separated, yeah? So control system, breaker, cable connection, and the buses in the internally as well. Stupid thing, switchgear temperature monitoring, permanent monitoring system. So instead of, there are some things that panels that you might have that you have to constantly monitor for temperature. And normally what we do, we just open it, measure it, and then close it, yeah? And if you have something like the critical panel that you have to keep doing this, sometimes it's cheaper and faster to install the sensors, and also safer because then you don't go there and keep measuring this. I don't know if you have it, but because normally there is a requirement to measure 1 time per year, 1 time per 2 years, obligatory, do infrared inspection on the installation, report it, and this most of the time is legal requirement. In Europe, it's I think 1 time per year. Sometimes it's more often depends on the countries. From insurance, yeah. Fixed absence of voltage testers, I will show you actually, because we have one sponsor which is not with us, but I will be representing from the Grace technology, so I can speak about this more later. Lockout tagout, of course, as a solution, it's clear. Proper tools, that's also clear. And we'll we use this. All of those things Let's say on the soft level, so it's not soft level. Most important out of this is how the electrical safety plan that actually should exist. That's the important, like I would say, like tick the box that at least you have it, yeah, legally. That's one thing, but it really is good when it works, yeah. There's working procedures, but the project design improvements. From my perspective, what I do, the biggest error or biggest issue I have is when people have a good intentions. They said, okay, well, let's make this thing safe. And then you start to, let's say, looking on the market, looking for the companies. Typically, people will start to look, okay, what we have, oh, Schneider, ABB, Siemens, some local companies. So we say, okay, let's call them because they build the panel. The panel is the problem. So you call people and then ask, can you help me this, make it safer and so on. So initially, probably 90% of them will say, okay, we can replace the switchgear for the new one because it's from money perspective, good thing, yeah, for them. However, the problem is, like I showed you on the Monday, that people sometimes can replace things one-to-one, which is not the goal, but the money are gone. So if you spend $1 million, whatever, or 2 million or whatever on doing your project, at some point you finish and you would like to calculate something. That's my point of view that I have, that people call me, Martin, can you calculate something? We have to check this. So I start to check and I said, yeah, okay, the selective is bad. The short circuit luckily is okay, because we have project when the short circuit is the problem and they're supposed to replace the switchgear that brand new that they installed. And we start to have a little bit discussion because why it's wrong and someone paid for it, someone told them to do it, doesn't matter. And then I go with the backlash calculation and we found out that actually they have a problem. But the way how they did the design doesn't allow to improve it without big investments. And now we have a problem because they spend money. Personally, I don't know any person that will come back to the boss and say, I need 1 million again. Yeah. Personally, what people will do is like, yeah, but Schneider said it's safe. And they will just leave it. They said it's safe, it will be no problem, it's a new one. And from everything you should see now, the condition of equipment is important, but backlash is not related only with condition, it's related to what you are doing. Yeah? So if you do stupid things or something will just drop something, doesn't matter if the panel is new or old. Yeah? Technically it should matter because the new one, it should be harder. But if you see the new switchgears with the bus bars on the bottom, with some metal covers, and then, oh, the cover is not there, and you just open panel and you see the main bus bars on the bottom. So gravity works one way, yeah? Whatever drops will drop on the bus bars. It's like, for me, it's technically the worst design ever, yeah, I've seen. On the top, yes. On the back, makes sense. On the bottom, even I have I think at CERN they have the case that they have a very big cellar, so they sometimes go from the bottom to the panel. Physically, they can just walk in and then look on this. And I said, what you will do if you have a panel like this, yeah? You look and the bus bars are there. Like the worst place to be. So this is important on the paper, let's say. If you can do something, do it before you order, yeah? Before you order, you check, you design, calculate. It's very easy to change something sometimes there's no cost to it. That's just my message to anyone is if you are planning something, do everything, all the calculation, RFID calculation, short circuit protection before you order something, yeah? Because some switchgear manufacturer, you will let it not get help because they will say, no, that's your specification, we just make according to specification, yeah? That's pretty much it. There are some other things, you can see there's a lot of things to handle this, yeah? If you have a SCADA system and motor operated breakers, you can have remote operation by default, which is almost 100% medium voltage networks works like this, yeah? We don't operate standing in front of the breaker, we just do it remotely or locally sometimes, but locally doesn't mean standing in front of the breaker. Yeah, safety switch or chicken switch, or there was a guy on the conference that we did last year from Ireland that he has a very brilliant system that he can rewire every panel almost and make remote switching very cheap. I don't know if he didn't license it to ABB, but then you just physically wire this to the breaker or coil, whatever opens the breaker disconnector, breaker or switch, if it's possible, and then you can just have a pilot that you just click yes, done. And because it's something that you just adapt, you don't keep it in the panel, you can take it with you, the most expensive part. So that it makes it easy and portable. Remote tracking systems are rather, they are existing, but they are rather not that popular because I would say power plants mostly, when they have a lot of big size, when they have huge amount of breakers and they really know, they use this racking in, racking out. Windows inspection, accredited PP, of course, proper one. And then we go to the point. We have, I like this one. I do a lot of those things. And I was recently, 1 month ago, on one side when we do a lot of improvements. And I forgot about them a bit. But we came and I have to make an update. So I asked them, did you do anything? And they looked like, no. I said, okay. So that's the other thing, yeah? Even if you do something, sometimes people will not follow it. So I try to change this approach as well. So to modeling we'll go later, but modeling the calculation. But if we do the model, that's why we do the modeling, because the systems are big. Small, big, or whatever, huge. So we need to have some help. Software is useful. Not every, they all work similar way, but not the same way. Doesn't matter what you are doing, there's always some tricks in the softwares. So we take small part of it, like this one that I showed you even yesterday. Very similar approach, because this is like the typical thing that will exist on almost all projects. Yeah? Like transformer, medium voltage, low voltage. And then we will look what we can achieve with those three things. So initially, if you look on the protection settings, the first thing is that we need to be allowed to even do any adjustments. Yeah, because sometimes relays are so old or weird. Or they might be not even old. They might be very simple relays, brand new but simple relays. Yeah, so that's this project design thing. It's good when the relay has at least few steps that you can adjust, or at least 3, and 2 groups of settings that can be used. Well, the controlled way. The old ones, they are not bad, it's that they just have a limited regulation. So when we go with this, and this is a part of very simplified calculation, I will try to show you the concept. So on the left one, you see the single line. We look mainly on this because on the main incomer, on the medium voltage, nothing will change, because I don't show you the upstream things. So there's a starting point. And then we have this thing in the middle is a TCC, time current curves. So protection, graphical representation for the protection settings over current protection settings. Yeah. And technically this is okay. It's not selective on the low voltage one, but it's selective on the medium voltage. It's not bad. But this is a real project, yeah. It's not bad. It's quite okay. And this was done in SKM, if you want to know, as a reference. It was quite okay, but then you look on the results. And we have a 10 kV station, we have 18.2, which is on the bus level. On the breaker itself is 34 calories, because there is no protection from the top modeled, yeah? So it will stay like this. On the low voltage one, we have a 20 calories on the bus, but 90 calories on the incoming panel, yeah? So if you have an incoming panel from the transformer, it's 90 calories. 90 calories is, in Europe, technically you cannot source the PPE, no one is selling 400 calories PPE. So we are above whatever we will. This is very dangerous level, yeah, by the way, but we are somewhere here. So what we can do? First thing, we adjust the settings. So what I did, I improved the selectivity for them. So I can keep clicking like this if you want, yeah? So you can see the difference. I improved the selectivity and change the setting, but improve the selectivity and improve the results at the same time, which is not always possible, yeah? Selectivity is a compromise or the grading of the protection of the way. So it's compromise for the time. So you want to have a nice separation time between the breakers or the relays, but then you go to the higher times. Yeah? The higher times means more energy most of the time. So, but I was able to make it better, faster, even for transformer protection faster, especially for the medium voltage faults. And then, but then at certain time we drop the energy. So on 10 kV we drop to 4 calories from 18, which is huge difference. Which is difference between having 40 calories set to 8, yeah? Big difference for the comfort when you are working. On the low voltage, we are already below 8 from 20, and on the incoming from 90 to 19, this is huge thing already. So you go to not having sometimes PPE to something that I can select, and I can even work comfortable with what we have. And we also improve the way how it works from the operation perspective. Yeah, that was the comparison if you want to see. The main thing was that the medium voltage was a bit higher for the transformer, so it can be much lower. and we don't have to use this inverse time curves.
You increase the tripping time.
No, I reduce, but I increase in this area.
The separation in the between the curves is bigger.
Yeah, because there is a minimum, something called critical interval time, which is 200, this is 300 milliseconds, 200, and between this and this is 100. But this one is based on the protection tables, because sometimes you can test this and say if it works by test. And between low voltage and medium voltage, you need at least 200 milliseconds. Proposed is 300 most of the time.
You move to the left, the PD1, DV1 phase curve. So
Yeah.
we're able to move the other ones to the left.
Yeah. Because the problem with the settings is that they are very random, and sometimes the whole sites are factory default. We used to have, I found out in Eton, when I was working in Eton, there was a manual. Eton has a lot of things from Woodward and from SCG. They work together, and in the manual it was written factory settings. And for customers, because we had a factory, mean that we did something. And I said, no, it means default settings. And the factory need to have a default setting because we do the quality check, quality testing. So they just set usually to the minimum. And I was wondering how those sites are working. I don't know, it's tripping. I said, okay, well, maybe you have to do some study and adjust the settings. So sometimes if you go to your site anywhere and you see the 10 breakers and they are set the same, like you don't have to look on the settings. You just see on the knobs and they will see like they're all the same. It pretty much means that nothing was done.
So in that case, you didn't change the relays, you just trying to adjust the curves and all that?
In this case, I actually changed because I have to change the pickup on the medium voltage. So check on the cables and so on. So I changed this. I changed everything here.
The relay?
Relay not. Relay was still the same.
Okay.
Because luckily they have a quite, I think it was Woodward MRI, like the smarter relay a bit.
Okay.
So I could do. But if you look, it wasn't that smart relay because technically it has a 1, 2, that's it. Normally if the setting relay is smarter and allows you to make like 3 groups or 3 steps or 4 steps of settings, then I will probably keep this this inverse time like they have, because it technically was possible. Keep it and then drop it and then go. But this relay was not that smart at some point. But technically we can do it because we have a low voltage breaker that will protect from overload. So the second thing, if you there is something called maintenance mode, which we can do also for low voltage and medium voltage. For medium voltage it's more complicated. For low voltage this is a part of the relay or trip unit, sorry, on the breaker. So if you buy breakers, sometimes you can retrofit the trip unit. Sometimes depends on the breaker. Like ABB has something like add-on for the new one, or this Equip Touch. So if you retrofit the relay, it's like maintenance mode on-off. Technically speaking, you can do it on every breaker because you need to adjust the settings. The problem behind it is that you will not allow people to adjust the settings, because then they will randomly keep playing with it. Yeah? Eventually someone will just, and they will forget about it, and they will keep tripping. Idea behind it is that you just reduce the settings by activating it on-off. There's, technically speaking, there should be also lockout, tagout, so no one will change it back, yeah? So you activate it, you lock it, and then you go. So we know that nothing will happen. It's a very simple idea. It's just override of the settings for time that you are there, because at some point you are working. We want to drop the energy to the manageable level, and we are, as a person, we are more important than the equipment for a moment. And if something will happen, eventually the equipment will stop, yeah? So just for the next 1 hour or 2 hours, we just reduce the trip, make it faster, yeah? But you don't want to keep it fast like this all the time, because it will be problem from operation. So this technically looks like this. So you can see it's not selective anymore from the downstream level, but it's fast. And I did 2 things. I did the same because this is default in the relay, in the trip unit in this, but I also make it for the medium voltage relay, which is this part of adaptive settings. So you can program the same function in the relay, just need to know what to do, but you can program it, which is custom made thing, if the relay is smart, yeah? So I have to propose change relay here. And then drop also the settings, but I didn't drop them to the very minimum. I dropped them to the point where we can still energize the transformer. Probably 1 out of 2 times we will energize it, because it's really on the bottom, if we have to, yeah? Because the transformer is running. So we drop it, and then you can see that the settings, the results are changing. So from the reference point, we go from 20 to 2, or from 7 to 2, depends how you want to and from 90 to 8. And on the on the medium voltage one, this one is 4.4 is no huge difference because it's still, this one stays the same. So it doesn't work, it's used here, but this is used for protecting transformer and the low voltage, yeah? And it's not used, this is done here purely because of this line side. And it doesn't work for the medium voltage bus, yeah? Otherwise I'll have to do it here and then drop it for the medium voltage. So it's already, you can see we are pretty much below, I have it because normally I use below 12 calories as a reference, so it's somewhere around 8 already here, so it's good. The third thing is that what you can do is install the separate system, which is arc detection system, the optic. And that was something that Dave was showing, that the relay, that's how it works. So you have a relay with the sensors, you install the sensors, typically optic the sensors only. And then the difference behind it is that this separate system that works quite fast. It doesn't really involve overcurrent protection settings, so you just can, okay, I can split selectivity, protection coordination from the arc flash. Now, so we have two systems. And this can be separate system or it can be built in the relay. So what it does when you install it, and this is important thing, so if you install it in panel, normally to protect this area, this breaker side, we need to trip one level above, which for us means medium voltage relay. Not always possible, but technically that's what we are supposed to do. In this case I did this. So the big difference is that we drop from 8 to 3.5. There is no big difference between, for example, this one and this one, yeah? Because the maintenance mode was already on the lower level, like lowest possible level for breaker tripping. So it's a little bit of difference, but not huge difference. But if you compare from the reference scenario to this, then we go way below 8 calories, actually below even 4 calories, just to play with those solutions. And this is relatively cheap still. And the last thing was the thing that David was showing, the quencher. So I don't know if I have the same video from Miko. Quencher, if you don't know how it works, quencher is a simple device. It creates the short circuit. If you create a short circuit in the system, at this point of the short circuit there is no voltage, or is nearly zero. When there is no voltage for the arc, and arc disappears. Yeah, extinguished. That's why they call it like unquencher. The extinguishing system, it sounds weird because it sounds like fire extinguisher, and it's not really what it does. Yeah, and then you also have to send a signal to the breakers to trip, to open. Yeah, because we have a short circuit in the system, but the short circuit is something that devices are rated for. If we trip it in 100 milliseconds, perfect, because most of the things will be rated half second, 1 second. They can withstand it. But arc flash will burn everything. Yeah, so this is how it works. This is the video, and I calculated, this is the same video that David showed you. What I did calculate is how much energy it is. So 300 milliseconds in this case was 10 calories because it was 30 kiloamps. This was 2.1, and with the quencher was 0.1. Pretty much, that's the difference. So you can see this, but the goal behind it is to reduce the energy. Yeah. This is nice test that Miko sent me when they did with the open doors. So what you do, normally you just put the wire and on the bus bars and try to initiate the arc. And the quencher is here, yeah, built in. So it has to short circuit those buses and kill it, and then send signal to the breaker. That's not how 65 kiloamp arc looks like. The only weird thing is that I told them they should do the now damage test after it, yeah, and show the difference between with and without. They didn't destroy the switchgear. But nevertheless, that's this is the fastest thing, most expensive most of the time. And I went very fast because I want to go to the calculation part. So if you have a question, feel free to ask. Yeah, I want to change it. Because yesterday we did one thing, and I want to show you, okay, this one. So this will be, you need to focus, I would say, because that's, so So we can do two things. I can try to connect later to ETAP to show you, but yes, on Monday I show you like what are the standards and so on. So for calculation, we will use most of the time IEEE 1584. And IEEE 1584, what's the time? It's good. IEEE 1584 is a basic standard for calculation, but it has some limitations. And it's good to know it, because if you would like to calculate something, and maybe if you use software, at some point software will tell you it's out of range or something like this, but if you do it by hand, you can just calculate, yeah? Nothing will stop you. So you need to know that certain things will not work, and this is like the cover from the IEEE, because they know what they did. They did some testing. They didn't do the testing above certain values and below certain values, so they will not tell you that you can use. But this also explains how far you can go with the calculations, which we will come back later to. I will try to open this Australian standard. So the model itself was from 208 volts to 15 kV. Tests were done to 4.3 actually. But they extended 50 or 60 hertz. That's why I can use this IEC 60909. 500 amps, because of the voltage range, 500 to 106. And for medium voltage, 200 to 65, because you will not see this value for the 15 kV network, most of the time at least. For the gaps, which means the distance between the conductors, we start from 6 something to 76, and for the higher voltages, it's going up to 254 millimeters. So something like this, yeah. It's important to know because also kind of tells that we go here, and then below 208 volts even you will not be able to use this model. So for the single phase. So I did already the example because I have to do the calculation for you in the background, so we don't have to do it live because it's manual thing now. So I took some example like a typical whatever panel. There's nothing like typical panel. There are some limitations for the enclosure dimensions. So we start with the tables now, yeah? We have some typical enclosures that IEEE suggests. If you go outside of the enclosure, which is, you will see how is it useful or not. There are certain sizes of it that they propose. And let's say we go like this, physically we will look on this, the breaker area they want to calculate. So 415 volts, we look on the main CB. The VCBB I will explain you in a minute. Voltage circuit breaker barrier. We have a distance like 600, 800, 800 deep. Yeah, that's pretty much the enclosure size, which is not the same as here. Gap is typical, so we take the typical gap from the IEEE calculations. So this is something we would want to calculate. Yeah. So normally there is a note in the IEEE that says that below 240 volts, which is interesting. Not 240 they wrote, and below 2000 amp, by, as they said, as a tested, it's unlikely to sustain the arc. Sustain arc means that you can create the arc, but arc will disappear because the distance and the energy and the voltage of the network is too low. It's still possible, but it's generally low. So it's hard to create, when it's just disappearing itself, then it just will not sustain and it will not keep for a long time, which means energy is lower than, which is something that if I would just take the plug out, you will see the arc spark or something, but nothing is happening to me. Yeah? That's because it's also disappearing very fast. So that's important to know that technically we should use it for the range of calculation, but the problem is that if you don't know where you have less than the 2000 amp short circuit level, then we need to model the whole system to find out. Once we model the whole system, then I can just do the rest of the calculation. It doesn't matter. Because most of the work is in the modeling, to be honest. First step, we have electrode configurations. Yeah, that's something I have to explain. Then in IEEE, because there was, in past it was 3, now it's 5. So we have something called VCB, VCBB, HCB, and VOA, HOA. If you translate it, it's like vertical circuit breaker, vertical circuit breaker barrier, horizontal circuit breaker, horizontal open arc, and vertical open arc. So this is the reference point that they used. It's, but I can show you some example. Technically, in one panel you have in multiple places multiple configurations. So you try to choose the common one and the most likely one. We choose the VCBB because on the panel that there was also covers on the top and down. VCBB for a moment, just to make it easier for you. Sometimes they are like HCB, so this is the HCB is the worst case most of the time when the electrodes are towards you, like this. This is the worst case situation for calculation for the arc flash, because it will be like extended or it will be concentrated towards you, especially when there is enclosure behind it. VOA, HOA is the same thing, just in open arc, so there is no enclosure around the panel, and you will see small difference because in IEEE there is nothing like the in between. Like this, for example, this will have a different transmission factor in DGUV calculation that Germany does, because it was full enclosure, partial enclosure, and open arc. In IEEE is like enclosure or open, yeah? There's nothing in between. Now, we start with the tables. I can open the IEEE paper later, but this new calculation from 2018 has a lot of coefficients, a lot. And there's a lot of table with coefficients, depending on what kind of equation you are using. So the first thing we started, we know is 108 to 600 volts. So we want to choose this one. I don't know if I have it, yeah, here. We choose this one. And that's the first step. We'll have to use them in equations, yeah? So that was the first step, to choose the right one. But you can see there's a lot of others, yeah? So that was the first one. That's the first equation that we have to use to calculate it. First, intermediate arcing current, and it's called intermediate because I especially choose 415 volts, so we do one step. But if you choose something like 6.6, let's say kV, then normally the equation works like this: that you calculate two, this one, and you interpolate the results in between. You just take the one result, second result, divide it, and then you have a value. Which is, and then it works for everything like this. So you do two calculations, and the third one, which is the final one. When I do below 600 volts, I can do one calculation only, which is easier for the example for today. So that's the first calculation. We have 10 factors, which was the table before I showed you, but we also need few other things. We need the gap between the electrodes, which we took the default, which is this one. And then we need, there is a bolted fault current here. Bolted fault current, if you don't know how to, that's why we use the software again, but generally, if you have a transformer, let's say 2 MVA that I choose for this example, and it has certain short circuit impedance, the easiest way to calculate it is like this. So it's technically nominal current divided by the short circuit impedance will give you short circuit current, the worst case short circuit current on the transformer. Assuming there is nothing else, no limitation, and so on and so on. You just need to get to the nominal current, and from the nominal current to the, so we expect 46 kiloamp, 46.4. That's what I need to make my calculations. I have a bunch of the coefficients, and we go next. So I made some Excel just to, because I couldn't download in the plane. So I have an Excel, 24 was the first step, and I divided the equations in two parts just to make it easier, yeah? So we have the first part of the equation was 24, the second was 1.1. I end up having 27.2 kiloamp arc current. So you can see that the arc current is not exactly, but it's like something like 60% of the bolted fault current, or the short circuit current, which is a big difference for the protection. So that's the one thing, because of the impedance and because of the gap. But there is a second thing we have to calculate now. So now we have to calculate the final arcing current, which is based on the specific voltage, because the equation was for the 600 volts. So now I have to recalculate it for the 415 volts. So that's what I did. So we find out final current is 20.7. So yeah, good to go, yeah? So it's less than 50%. Now there is something called variation factors. And this is something coming from the long time, from practical approach, that this is E arc mean, and you can see there is some factor to it from this final arc that I calculated. The problem behind the arc is that arc is not something that you can easily predict. And from the test, as far as I discussed with all the guys from the IEEE, that from the test they find out that you calculate something, and it's very likely that your calculations are plus minus something, because we calculate very precisely something that we estimate, yeah? So we are somewhere plus minus, and it's very likely that you are a bit positive on the current, and if you reduce it a bit, you might find out that your tripping times are much higher, which I will try to show you an example later if I can show it. So it's more about the protection. We just try to find out the lower current and then see if this lower current is not a problem for the protection, because you might be on the edge of the settings. So this is like double check. If this is not the problem, we come back to the other one. So we calculated this was 18.9 comparing to 20.7, so 2 kiloamps less almost. And then we go and check. And my idea was to show you like this. So this is the typical situation that your arc current, the normal one you calculate, is somewhere here, which you can see is like, it's very close. It's not that you just make, at least you make a small mistake in the calculation. It's not 20 millimeters, but 25 or something. Then your current will drop and then you are somewhere here. So this is what we want to check. If 50 milliseconds is not too positive, maybe we have 300 milliseconds tripping time. And that's why the software is useful, but so we can double check this. Okay, it's actually not 50, it's 300. This is the worst case situation that might happen for me. So that's why this minimum current is used. Second thing, so we go to the point because now we have to calculate the energy. So we need few things before. So we need the correction factor for the enclosure. So you've seen that I have something like, and this is tricky part because the enclosures has the reference values that they tested. Everything is based on those reference values. So now we have to recalculate something called equipment enclosure size, which is this, equivalent enclosure size, to get this point. Equivalent enclosure size, which I don't know if I have this here. No. It's the recalculation factor for the size of the enclosure. There's like very simple equation, which is before. When you calculate that the size of this comparing to the reference size will give you something like 0.20 whatever coefficient, which we will use later here, based on the table again with the coefficients. It's not very user-friendly for calculating by hand. The previous version was much easier. And then we go to the point where we can finally calculate first energy, which is, at least if I specifically choose this one, so again 13 coefficients, I specially choose this one because here we have to calculate 1, 2, and then recalculate in between. So we have 415 volts, we calculate it. I have a minimum arc, I have a normal arc, I have this bar coefficient as well. And where's my calculation? Did I stop here? Because it was 20 something calories. Because when you put everything in, there's the same coefficient factor that I used in the previous one. For this, there is one table that you use from the VCB, and there is additional coefficient factors for K13, which I have, I think, in Excel. And when we calculate it, then you end up with having something like 25 joules, and which turns joules into calories, which was going like 5 calories per square centimeters, which I have to open Excel now because I think maybe I didn't fill it in. And this will end up your calculation on the energy. And the last thing you have to calculate is arc/bond hour, which is also like this equation, but luckily we just use the same coefficient factors with just a different equation. So you estimate the difference, how far you have to stand to reduce the energy below 1.2. I have to open the Excel file because maybe I didn't do it in presentation. And that's pretty much how you calculate the arc/energy for one point. The problem behind the hand calculations that are not, so they are harder now, but the problem behind this is that if you start to do this, and I have also a lot of Excels, but the problem behind it is if you start to do this, and we do not 1 or 2, 3 points, but we actually do the system. In system, you need to do different configurations. Yeah, so we need to have a configuration with generator, with minimum, maximum, with the battery storage working, without, or with PV. So sometimes, like on DC systems, we'd have 12 configurations of the network. Then we recalculate the short circuit, then we have to recalculate the protection, then you have to do the recommendations, which is additional 12, yeah, with recommended settings and solutions that you do. And then someone will tell you, no, Marcin, but actually we changed this because it's not true, and you have to change this, and then you reconnect the cable, and every result is changed. So in Excel, this is probably something like 2 days of work, just to update something, and in the software it's just, okay, you reconnect it, you rerun everything, is few hours of work, maybe not more than 2 days. So in my feeling, that's what I see, that Excel calculation, hand calculation are just this encouraging people from doing any updates, because they know that when they do it, it's like a lot of work. And we have projects for data centers that constantly get the revisions. We finish one and they're like, no, it's this, we changed the settings again. And I said, Jesus, because it takes 4 days just to update the model, because model is huge. And they keep going like this. So you can imagine if you try to do this in Excel, then you have a lot of assumptions at the end for the tripping times, everything else. No one will keep checking this. And it's very easy to overlook things, because if you overlook things, you would just to tell to someone, yeah, it was 50 milliseconds. And then we check it and it's like, no, it's not. It's actually 2 seconds for you to trip here. And it's like, how? Because again, that's why the digital models are useful, because then you can see, no, because this part is not fed by 2 generators. It's fed from one side, but not from the other side. And that makes huge difference for the short circuit current that you have to trip. It's also logic how the things works. Yeah. So I can open you the Excel that I did. I think I have it somewhere, because this will be the second part that somehow I forgot to add here. Here it is. Just let me move it here. It's a fascinating Excel. It's because I need to. Let me do one thing. I will show you from here, because otherwise we will be struggling. Where's my here? I will do one thing. Okay, so the whole calculation idea, but I need to remove one thing just to show you. Just give me a second, because now I don't see this thing. Let me just return back to the here. Okay. So the whole idea behind it was to show you one thing. It's possible to calculate in Excel. I just made it when I was flying. So we have 27, 20, the equations on the right side, all the coefficients, factors, and so on. This was the part where we go with the height and EES, this equivalent enclosure, what's called sizing factor, and then the correction factor for it. And then at the end, because of the tripping and the working distance, there we can go, you can see this, yeah? It's like, there's barely a place to put it. Then you end up having the energy having 24, which is transferring to 5.778 calories per square centimeters. And the arc flash boundary was actually 1 meter for it. And technically that's where we stop. If we do the different voltages between, then we have to do 2 calculations and then recalculate it back in between the value. That's how the whole calculation works. It's not impossible, it's just if you look amount of the coefficients that they use in this new calculation from 2018, yeah, it's not bad, it's just annoying, yeah, I would say. Someone has to be really Excel smart to do it in Excel, or do some nice tool. So it's not that it's not possible, but there was one more thing I can show you, because I did. So if you go to IEEE 1584 as a standard, so you can get all of this. I just copy paste it from here, so you can see it how it is. I didn't rewrite it. So technically, if you go here, it's nice to read the top part of it. Let me go back, and then you have all the calculations. And there is, I think, one interesting thing, all the steps. So it's technically written here how you're supposed to go from in this point 4.3. And there you have all steps that you have to do. So if you follow this, technically it will be okay. And there was one thing I want to show you that was mentioned here somewhere, that you can see this interpolation part. Give me a second. Here. So here is the interpolation part. So you have one arc, second arc current that you calculated, and then you recalculated the one in between, here. And the same is with the energy. So it's always like the interpolation between 2 points. So you don't specifically calculate for 6 kV, you calculate for 2.7, for 14.3, and then you recalculate the point in between. That's how the calculation works for the IEEE 1584. And then you can go through it, because it's actually an interesting document if you want to read. But and there is an examples, working examples here, so you can go through this as well and test it with even how it works. So if you go through this one, then you pretty much will have an idea how this works. But I want to show you one thing, but I need to find it out. Just give me a second. My colleague sent it to me, I don't know when. Wait, let me just reshare it back for you. And I can dig out one thing from this. I should have it somewhere here. I want to show you one standard that he sent me partially from Australia, which I think is interesting to show you. Just Goffrey, where are you? Here it is. Let me just open it. And move it aside. Okay, I need to go somewhere here and I will show you this. So there are some required notes he did, but there is one table which I want to show you, and we have to return this. Yeah, so let me go back. There was this discussion about how this limitation works. And there's the standard that exists here for 2023. And if you look, below 63 M is written PPE based on electrical risk assessment, whatever it means. And here, it's a bit strange thing, because everything is like 4 which is also isolating normal condition. There's like some risk assessment involved in it. 4, 4, 4, 4. And here is like 4, 8, 40, 75. It doesn't say what kind of energy you have. It just say if you are below 2000 amp for 100 volts, then you need 75. Which it's an interesting table to see in the standard like this. And no intentional protective device delay. So I think it's something that someone tried to do something like the table method. That is in an FPA. They're supposed to help with something. But if you have no international protection device, then you will not have 75 calories. That's what we did before, mitigation, yeah? So it's weird because this just tell you 4 or 75, yeah? It's not bad, but just, I have no idea what was the intention behind it. I just found it yesterday when he sent it. And this is like the working on the racking, live work and so on. Authorized live work. But not necessarily like below, as I showed you, like it doesn't have to be 75. It can be like 2 calories. Because we can handle this, yeah? So it is a bit strange to see this, 4836 for 2023. So I asked him to send me the full one so I can see how this generally refer to the rest of your standards. Because I've seen also in Ausgrid some different things, but Ausgrid is a private company, so they can do something for themselves. It's a very typical thing that the distribution companies have a different approach than the industry. That's what I said on Monday. The transmission distribution goal is to transfer energy and don't stop. And they do live work. In industry, we actually want to stop and do maintenance, and we don't want to do live work. That's a small difference, yeah, on the approach. And also you can see this in the electrical safety plans, because they write it a little bit different. And if you try to transfer it to the industry, you start to struggle because that's not how they work and that's not how we work. Technically speaking, I have like the still idea, that's what I said in my committee in Poland, that they should technically split industrial work, electrical work, and transmission distribution work. Because those are really different groups of people working in a really different way. And they typically, they are past government companies all the time. So they are very all the time bonded to the government quite often. So they have big influence on the standards that are written. And they write those standards for themselves, for their own, let's say, pleasure, I was going to say, but just to make it easy for them. And then people from industry has to use it. And like we have a procedure that involves at least 2 people. Technically 3, but then you can join also at least 2 people, and sometimes there's 1 electrician. So you have to like play around how to do it, yeah? So we have all the permit to work done. So that was interesting part. And I can show you one more thing. How are we about the time? 11:34. So I'm quite fast on this. We can do 2 things. I can show you also the working example for the battery for the DC calculations. Because I did, I think I have it somewhere. I left it there on the presentation. If you are interested. And then we can also later, we can just start it up and I can show you how this works on the software. So we can just build one small thing and just see how this affects, how it works, if you want to see. Is it SKM or ETAP? It's up to you. But I have a feeling that I'm a bit too fast. If you have any questions, you can ask, yeah?
I was going to ask you, how are arc flash calculations carried out on anything over 15 kV?
With above?
Yeah.
So not with IEEE, because IEEE is up to 15 kV. So if you want to go above 15 kV, you use, yes, on Monday I said there was a technical report from EPRI, Electrical Power Research Institute in US. They wrote this report, and based on this report there are calculations done. So you can use this, of course, as a paper by hand, but some softwares, I think ETAP has it built in. SKM has something built in similar to this. So you can use some softwares. Not every software has it, technically speaking. Or you can use the roughly method, which is a base calculation for arc flash, but it's very conservative and it will give you just very high results at the end. So it's not what we want. Yeah, you want to be. It's not the goal to be as low as possible to choose the positive calculation. It's just to be as close as possible to the reality. Yeah. So if we can have low, and it makes sense because if you look on the high voltage arcs, they are a little bit different, yeah, than the low voltage one, and they behave a little bit different. Doesn't mean that they are not dangerous, but this energy explosion factor is a little bit different in medium voltage, especially in the high voltage networks. Not even medium voltage, but the high voltage networks. I was going to show you one more thing. So there's a fascinating world of calculations, yeah. I would say the most work is done on the modeling. So it depends how you model things, and I can show you this, the one. Okay, we can continue on this one, I think, where I finished. Because that's the second part I did for the, I just took some part of the presentation from that I did for the ETAP itself on their own conference. This calculation was based on the comparison of the DGUV and IEEE calculations, how they, why did it change? So there's the same story. I took some of the existing, why it goes automatically? It's the existing project, and I took few, because I calculate complete project for this, with IEEE and with DGUV, but it's not about the comparison for you. I want to show you one thing, because I have some few of the things in it built in. So normally it's like the thing is, that's why again, software is useful. We have 4 scenarios, existing recommended. So min-max, min-max, just to limit it. It's limited to 1 second, not to 2 seconds, because DGUV have a limitation for 1 second as a tool, as equation. So I limit it to compare it properly. And then we have you don't have to look at this, but there was some configuration done for the DGUV calculations. I don't know why for the DGUV calculations and then for the IEEE calculations. So there was a main, because that was for the software people, yeah? And the main issue was that I modify a few things based on the 1 second, not the 2 second rule that ETAP has. Some of the companies, they will not allow you to use 2 second rule because they want to see those crazy energy, because crazy energy will give you the fast check that something is wrong with your protection. Because if you limit things to 2 seconds, you might be too positive and you might say, okay, it's like 40 calories. Actually, it might be not 40, it might be that it would trip in 800 seconds, yeah? And you just start to see this few thousand calories or something, which is not fully true, but it's not the exposure for the human. 2 seconds is like the cap that you can keep as exposure for the human, but the overall energy might be much higher. Okay, this is just the overall. I want to go because I have on the later part the DC part. I did the comparison. They were very similar at some point. Not all the points. So if you do different scenarios, then you can start to see that in certain scenarios you have a different. I don't know what I guess. Is it maybe there's something lying on this? No. Okay, I don't know why it's keep going automatically. Maybe I have something on the presentation. So you have multiple scenarios, then you can start to see the worst case. And the thing is that you can see that there is like drop from 3 to 12. Yeah. When we do recommendation for the setting, sometimes you also increase the energy. We try to just keep it in the same PP category area. Because if you have a 2.5 and you can make it better from protection and make it 6, it's not good from safety, but it's like overall you have the same PPE still on yourself. So it's acceptable, let's say, solution. But then you can see from the overview that you have a lot of different things that can happen. That's why the different scenarios are important, because you might find out the generated scenario is actually much, much worse at certain panels because of the lower short circuit current. DGUV was the same. It was like, we can skip this part because I doubt you use DGUV. Then we made some comparison for the one case, and that's the most weird thing on the DGUV, that they went very, very high to the, oh, we don't have a PPE. And that was my whole point on this. And I used some few things for them. That was the example also how to improve. That was also from existing project. And that's one interesting thing here. My main problem on the project is not really arc flash all the time. It's protection. People have, generally that's the existing case. And this is bad. You keep tripping medium voltage. So it's barely possible to energize the transformer even. So we keep tripping medium voltage. No one wants it, because in most industrial cases you have to call a different guy. And if you have to call in 2 a.m., like, okay, who will come? And the whole production is stopped. So protection is one of the things that is existing constantly. So you want to be well protected. And my change is like that I try to make it protection correct, and then we look on the arc flash. Most of the projects, sometimes the customers, they will allow me to say, no, Martin, it's more important to reduce the energy. So I have to double ask if they are fully aware that they might be going for the medium voltage station 200 meters away to re-energize. The problem behind it, I don't know if you see other problem behind it, if you are not selective as well. Because the biggest problem is not that it will trip. The biggest problem is to find out what actually trips. That's what we have on the cables yesterday. If your cable is damaged here, and this relay trips, then you expect the problem to be somewhere here, yeah? If you have a 5 meters of bus bars and 10 meters of cables, it's easy to find. On transformer, it's harder, yeah? So if this trips, because you have a fault here, you will spend quite some time looking why. If this trips, because it's selective on this bus, and you go to the low voltage one and see like, okay, I see why it trips, or it took me half an hour to find out, but I know it's supposed to be somewhere here, yeah? Because we know things are selective, or they work properly. So I will look on the panel, so you just try to find out what was the goal, yeah? The cause of the fault. If this trips or this fault, you will not first think about this. You will just try to find out, okay, medium voltage cable transformer, you will look on this, and you will spend a lot of time. Imagine this has 200 meters, yeah? So you have to locate the fault. You just try to locate it. There's no fault. And it's like, oh, no, but medium voltage trips, so it has to be medium voltage. And you just keep looking, yeah? So this is just a waste of time, big waste of time, especially on bigger networks. So we try to make it easier for everyone. That was the same, just to improve it a bit, just to make it, but then it just improved the selective, but also was changed energy higher. So then we have to go with something else to handle the arc flash, yeah? I'm supposed to connect to it, but I will do it later on the next session. For the DC, because I've seen that some people have a battery storage, yeah, system. So for the DC, there is an interesting case. We have also, I use the UPS because we do data centers. And data centers have like 2 megawatts UPS, which is very similar to the container that you use on the battery storage systems. I have somewhere battery storage system, but I don't have it like well prepared for presentation. So that was one of the case that we have on one factory. There was actually factory support. Interesting thing, I don't know if you know, it's something which is called dynamic rotary UPS, drops, which is spinning. It's something like the what's the name in English? There are synchronous motors used in the grid to support the frequency. As a frequency support, like huge one, like 200 megawatts and so on. So they just keep spinning, and when something happens, they're like, "Ooh, yeah, we support this frequency, yeah, for a moment."
Flywheel.
Yeah, but the flywheel is the droops, is the rotary UPS, and the synchronous. There was a name for it. I just lost it.
They run a flywheel in a vacuum.
Yeah. So they're just like spinning just to give you the reserve for the frequency, very fast frequency support, but on the grid level. Yeah, they are not like 1 megawatt; they are like 200 megawatts motors. Yeah, and So because UPS also can be used for this, for the frequency support, yeah, on the other hand. Nevertheless, we have a battery, we have a system, and that was the system as it was designed physically. So it was going here, common bus bar on the UPS, 3 racks, each has a fuse, and nothing in between. Very common thing, and the VRL batteries. Of course, the biggest problem on modeling on this is just to get the battery data, and you will not believe how hard it is. Just to find out what the internal impedance of the battery is one thing, but for the lithium-ion batteries, discharge curve of the battery is almost impossible to get. Super hard. We did for the automotive, and I even asked the automotive as they are buying things for BYD, I think, and asked them, do you have any data on the battery that you put into the car? At the factory, the assembly, they didn't have nothing. Yeah, they have like some weird chemical things, but I said like, yeah, but that's not what we asked for. So it was super strange. So we look for the battery type. Luckily, the UASA has it, so we find out. I don't know if you can see interesting thing here. That's not the DC fuse. That's the AC fuse used in the DC installation, which is not ideal, I would say. Technically, it can work sometimes like this, but it's not proper way. Yeah. So we have this. We find out the short circuit current. We know we have an internal impedance. We know the voltage will be variation because of the loading. On the batteries, then speaking, is very hard to. You will not keep the battery load like they keep like 20% charge, 50% charge for storage. It's never go to. You cannot discharge batteries. There is nothing. This is like the tricky thing on the DC system, that on the battery system, that you will never discharge the fully, because you can discharge it, but it's like 30 minutes, and then you have to charge them back. Otherwise, they will just keep dying, and eventually you will lose the capacity. So there are some few methods to calculate the maximum power method. Is the simple one, when you just take the 50% of the short circuit current. Then there are, and this is very conservative. There are some. This is generally pretty much the same Ammerman calculation. Nice paper to it from the Daniel Doan. And two things which I use are Stokes and Openlander calculation. There's one more from Paukert as well. Mostly I use this one. Fun thing is that something which is referring to DC test very often is not tested at DC but AC, which you will find in the papers. So the proper DC calculations and DC testing still has to be done. As far as I know, the IEEE is working on it, but slowly. DGUV did something, but because I tried to ask how they get to the DC calculation, what was the testing, and they're like, there's no answer. So we don't use it. Different models. DC behaves a little bit different than AC. So if you look on this, it's a bit when you are modeling. This is from IEC. Where's my 61660? I think supposed to be. So from the IEC perspective, from calculation, you look on different models, which is like the capacitor, or is a battery, is it the motor rectifier, how they behave, what is the discharge, and so on. The short circuit power will be. Yeah. How much time we have? That's good.
We're starting at 12. The other one. So.
Okay. So this is something how you create the models technically by the standard. Yeah. When you would like to create DC model for your short circuit calculation, because we need short circuit calculation to go to the protection and arc flash later, yeah, which is 61660 if I remember correctly. Different model. So from ETAP, that was modeled in ETAP. So the thing was that we have a battery. This is the calculation point for the battery itself. Let's say as the entrance of the battery. Cable, DC cable, fuse, and we calculated the fuse connection because it was a panel. For the fuse, DC and common bus. And there are like 3 strings of it. And the thing behind it was that if you look, it wasn't like huge one core of the inverter. So even if I kept the calculation at 2 seconds, we end up having like 25 calories at on the inverter itself because of the battery short circuit current. The thing was that mainly it was because of the fault and the fuse size. A bit, and then you multiply it by 3 because you have a three racks. So the next thing what could be done. So I increased the settings to 60 seconds just to see what will happen, because 2 seconds might be optimistic. And that was, as far as I remember, there was a closed space that they had when you actually was hard. Not that hard, but it was limited. It's not like this size of room that you can escape. You have to really like go back. So if you increase it to 60 seconds, you can see this didn't trip at all, but because it's battery, battery will not trip. It will keep going until it can. The fuse will actually trip in 5.7 seconds. So that was first surprise, and then you have the same time because they are like keep going from the same 3 levels. So you see that actually 5 seconds is the tripping time, or what we calculated. But you need to get the cables. Everything right, because if you don't, then the calculation might be. There are a lot of, especially if you have a short cables. This will influence a lot the calculations on the DC. So that's how it looks from the protection perspective. So it's AC fuse, it's not DC fuse. I have to remodel it for the DC purpose. If you check on the short circuit current, then you have 2 steps, depends on what will be the tripping time. So 3.3 and 6, there was one more that we'll calculate later. So you can see the trip time for the 6.6 for the short circuit was approx 85, but for the arc one was 5.7. And no side protection on the battery side. Sometimes batteries has the protection built in between the racks, but not in this one. So first solution, because you can do things with it, So you can have the AR fuse, rapid fuse, which will just reduce the tripping time from 5 to less than 1 second. Still not ideal, but we drop the energy, So we drop it. If I keep the 60 second, we drop to 12 calories. And here we drop also, I think it was 12, because what is maybe not logical for you now, why this common is 12 and this is the same. That's because remaining 2 also adds to this bus, So the fact that you operate on this one specific fuse, it doesn't mean that it's only energy from this one battery, it's also from the other batteries, It doesn't matter if you switch here or switch here, The second thing, I was investigating if we can reduce the fuse size, because it was bigger. I think if you don't see it, I don't see it here. Well, it was 450 AR type, so 450 AR, so you can see the outcome that was just faster, It's like has a little bit different characteristic. Relatively simple thing to do to make it still work. Then also reducing the fuse, but it's always on this kind of system it will be hard because you need to be very sure that you don't need this that much energy. So we just tie this more precise, And it can give us a bit of time. So you can see that tripping time was dropped to 0.1 second, which is a big difference, 10 times almost. So we see that we now are at 2 calories instead of 12. So this is getting, you can see 230 calories on the battery, which is not true, technically speaking. So that was the 350, so we shifted a bit, but I doubt that was not really like the great solution for it, And what else you can do, and this is something which will happen sometimes on different UPS, but this is not solution, this is more like choosing the UPS later. Instead of having 3 strings per core, you can have 3 strings per 3 cores, and adjust a little bit different. And this will just limit the amount of energy that is accumulating from the others. So it goes directly, not the common bus, but each specific core gets their own battery rack, let's say. So, but because it depends how they design it, sometimes you can just design one line, common bus, everything is connected to it, but it's also accumulating at this bus at the end. And you might not have to do it. So that gives a bit of change. And I think there was one more thing in it. Yeah, because technically all of those things are important from this perspective. So depends. In the DC systems, everything is, I would say, more modular than in AC, because we have a container, modular container, batteries racks, and it comes like product, almost. The same is but you connect this product to your network somehow. And also with the cars, with the EV cars, which is like, they are getting 900 volts DC bus, even more. In the trucks, they go above 1000. Fun thing, if you don't know, in the automotive industry, there is ISO standard. Everything, whatever is above 60 volts, they call high voltage. 60 volts DC. So It is a fun thing because we did for the automotive calculation for the EV, and from this perspective it was weird because they said it's high voltage. I said like, no, it's not. And I was talking with them, and I just randomly touched the batteries. I said it's not high voltage. And they were like, what's happening? The idea behind it was that we calculated a big battery for I think for Stellantis, and they have an assembly process and they have an accident. That's why they came to me, because of the accidents during the assembly. And the idea was to find out what the problems they have. And when I was on the side, they have like 9 stops on the production. And the thing was that they were all wearing the electric shock gloves. I was like, huh? Because they assembled the battery. The whole battery was approx 400 something 80 volts. If you assemble everything and charge it 100%, it will be 480 volts. And I was like, okay, so shock hazard exists, yeah? And I asked them like, how often do you have to, because they work 8 hours, yeah, in rubber gloves. And I said like, yeah, they are not sweating. And they're like, yeah, we do. And then I was walking with them and I was just randomly testing the gloves. I just grabbed them and just roll them like here. And it was like, tss. So like, yeah, tss. I was like, I don't know how much money you make, but you will not, like those are not the cheap gloves, yeah. So my idea was to do one thing for them, which was a very simple thing. I just reorganized the manufacturing process a bit. And still they have one more accident because I missed one step which I wasn't aware. So because they were like assembling the packs, group, and they went with the full battery for a long time. And it was just, at one point I said like, hey, because they were not fully charged, I have to measure, like I spent like 2 hours measuring those batteries walking around. Also, we find out that they have something like the kill stop in between the batteries. So they split the battery in 2, and in between there was a contactor, something like on the like when you hit the car, something that stops the power, yeah, like the dynamic one. So they had the same, which is normally open. When you start the car, it's just connecting back. When you turn it, it's connecting back, and then there's like complete full voltage on the battery. It took me 2 hours to find out because they couldn't explain, because I was measuring, it's like, I should be voltage like that, Jesus. And I just find out during assembly that I said, what this thing is? It's like, oh, that's the contactor. I was like, what contactor? Because it was not on the single line. I was like, okay. So I found this. We organize a bit the battery itself, that I split the batteries. There was like 2 connections that you can just remove. And they were going below 100 volts, I think 90 volts. They were going all the process, and at the one step they have to reconnect back, and then they didn't have 400, they had like 200 something at some point when they were at the final step. So I said, okay, that's the guy that needs gloves. Everyone else doesn't need the glove. They will have the arc rated gloves because we were calculating for the arc flash, because that was the problem. And they actually did one stupid mistake, because I have to go there back after 1 month, because they told me that there was an accident. I said, how? Because we calculated it was almost impossible. But there was one step before when they connected 2 batteries together. I think each battery was something like 48 volts. They connected 2 batteries together, and the battery has a plus-minus connection very close to each other. And normally the process was they have to open one, connect one, screw it, open the second one, connect the second one. So it was like, they remove both of them, and they just try to connect, but then you just put the copper connection, yeah? So they put the copper connection, and then I think when the guy was screwing, it was like, and they just make the short circuit, yeah? Ideal situation. It took me 1 hour it was like Dr. House, just to find out everyone lies. So I just find out, like, that's okay, that's what you did, yeah? So there was also a simple thing where I just said, okay, remove one link and you don't have a connection. So again, I have to do it, and I have to just look at them and it's just like, nothing will happen. I know. And it's like weird thing, but that's with the batteries a bit. That it very depends on the state of charge. It depends on the modeling, at least. It's very crucial for it when you model all the cables, especially cables. Even the short one, like half meter or so, you have to model this because it will influence the L side for the time constant. And it's important because then your peak current will be much lower because of this. So it's important that you not assume that it's a half meter so we can ignore it. Like, you have to really add it, because those are very, very small values that you will actually calculate on the impedance. And that's important for this. And this what? That was something else. So that's for the DC systems. I have a feeling that I am going too fast. Later we can connect. I can show you how it works in ETAP when we do the calculation, how to model it. ETAP or SKM, depends what you want. Depends what I can connect to. And that's pretty much how calculation works, combining with this Monday, check how the whole ArcFlash study as a process looks like. There is one important thing that I'm not talking because we talk about the calculation itself, but most important part before calculation, that's what Sam said, what goes in goes out, is data collection site visits. Because whatever you collect from the site or from the documentation is probably the most important thing that you use. Because if you have a bad input, your output is worthless. Yeah? And the same is with on the data collection side. You don't have to do it technically speaking, but when you go to the site, you actually see things. Yeah. So you have to judge it, but also you can give the feedback to people. Like you go to the panel, I can use the fridge. You go to the panel and you open it and you just see there are no covers, nothing in it. Then this is like the problem. Yeah. And it's not something you have seen in the calculation. You just have it. Yeah. So there are a lot of things that are not related with calculations, but related with electrical safety. And just to keep in mind, not everything will calculate. Yeah. And sometimes even if you calculate something which is wrong, you can fix it with the procedure. So this hierarchy of controls is useful because you can fix it with procedures, just saying in the generator mode, when we run generator, we don't do any maintenance. You just operate, but we don't do any maintenance. You are not allowed to do the infrared scanning now. Yeah? Otherwise, you have to prepare permit to work and think how to make it safer for you because we expect 70 calories on the generator side. Why not? So there are a lot of things that you can have it, and those are like multi-layer systems that you work with. It's not only about the other fun thing is, no one requires calculations. This is just ArcFlash risk assessment, or in many cases, it's just saying we need to allow people to work safe and give them proper protection control measures to make the work safe. Just calculations that the AI normally do is just the cheapest and simplest way of doing this. And that like something that you can repeat easily later, because once we have a model like the one here, you can imagine this is not the small model, yeah? So once you put a lot of effort to do it, let's use it, yeah? Because you can do a lot of other things with it later, not only ArcFlash, load flow protection, harmonics, and some other things. And the thing behind it, that once you do this, the next time you do it, like we do now refreshments for some customers, so next time it's like 20% cost maybe or something. Because you already did site visit, you did everything. We just work on the differences. Those differences work is weird because an FPA says on IEEE generation like you do calculation latest every 5 years, which for most people is like every 5 years, which is not fully true because you have to, when you change things, you're supposed to update this. But you will not recreate the model again and again and again because it's like not cost effective, yeah? So usually it's like once we do something, then you just keep updating this and you keep it low. It's easier, faster, cheaper, I would say, on long term, and but also easier to get the results. Yeah, easier to get the values, make it more predictable. Also easier to, I don't know how many of you have to do it, but just to prove that okay, we follow the best thing. Because once you do your calculation in Excel, and if you make a mistake, and someone will prove that you make a mistake, because eventually they will come to someone like me. Someone will say, yeah, this is shit. Just a nice way for the code. Then people said, yeah, how often you do this? Oh, 1 time per 5 years. And then it's like pretty much end of the discussion because it's very easy to make it's like the weird thing. I will not discourage people to doing this. It's good exercise if you do it. You just probably find out how many things you have to collect, what data is missing. This, generally as a single line, is the main thing at the entrance. I had this first stop as a scope of work, a contact. This is sometimes the biggest problem we have. Because I ask, like I have one customer now, I asked, okay, can you send me the single line for your site? If you have anything, I don't ask for like beautiful single line, I said like whatever you have. It might be 40 years old in your substation, just make a photo, send it to me, maybe draw it, scan it, whatever you want, send it with the pigeon, I don't care. Just send me so I can have a look what we are talking about, pretty much. To be honest, I even quoted from the Google Maps, which I said like, I don't know how you want me to do it, but no, that's the location. So like, yeah, okay, let's try and see. But the thing is that we need to know what pretty much the installation is. and this is legally always required in most of the countries, that you need to have a up-to-date single line diagram. One of the most important thing, and this is for lotto, for switching, because like they were showing the switching. Who cares about the switching program if your single line shows you E2, E1, and you pop up on side, it's like, what E2? Everything is like field 1, field 2, and then you just say, I have no idea what I have to do, yeah? So the step, the checking, revisiting what they were saying was good, because you go to site, and you actually find out that we have often like transformer 1, transformer 1, transformer 2, because people are ordering from different companies, and they will have transformer 1, transformer 2 on the drawings. And they have like 4 transformers 1, 2 transformers 2, some transformer 3. Everything is called low voltage switchgear 1, Q1, Q1, Q2, and I said like, yeah, but we all have a problem, because in the softwares like this, you cannot use Q1 as a name, because it has to be unique. So you have to be creative to make it LV1, Q1, LV2, Q1 or something. So it's easy to identify. There's other story, but single line is the one most important thing that you should have, because it unlocks a lot of other things. And if it's not up to date, probably it's not a tragedy when it's existing. If it's a bit not up to date, it's okay, because you can make it easier yourself. If it's just like 20 years old, it's very likely it's useless. So it's good to keep it. Yeah, we work now slowly, because, for example, the model from SKM or ETAP is not, it's good as a indication, but it's not really single line diagram. It's something like the single line we create for the model, but in the model you skip a lot of things, because you don't have to like drop the RCDs on some small feeders on low voltage, or sometimes you don't have to show all those metering points, because they don't add anything for the calculation. So we just keep skipping those things. So it is good indication how the system looks like, how it's connected, but from the really being a single line, it's a good starting point, I would say. Yeah, it's not exactly replacing single line, but if you have it, then it's probably giving you already some kind of overview. That's what we are talking about. And when you want to see some connections and so on, how it's connected, how it's used in different connection type, but it's not exactly like the CAT type single line. And this is one of the most important things, because if you go to site, this is what I see most often. We just see it and it's like, okay, we go to one station and I see like it's not 1 or 2 transformers, or one is gone or something else. And I have seen that people tend to have this kind of belief that we have documentation. And I always like, we always welcome when the documentation is available, so I keep sending this. So when they send it, we look at it, we prepare, we go to site, and then we start to go through it. And a fun thing is that, for example, you don't have it here, but what I do, I just have a list, kind of left, right, that we check on what's in the switchgear. Let's say 25 feeders plus incomer. So I have to find 25 feeders, and incomer I see. So 25 feeders I have to find in field. And we just keep looking for it, yeah? Cables, protection, everything at the panel. And sometimes we just left with 2 that no one knows what it is, but it's energized. And one guy just randomly once switched it off. And we're like, he said, wait. He was looking on the factory, because it was like kind of in the corridor, and they like, switch it off. And it was like, 1, 2, hey! It's like, okay, he knows, we went somewhere. But normally you will not do it, yeah, because it's like fun thing, but it's stupid to do it. Normally it's like something that, and I see that people have a problem to identify later. That they are super convinced that that's this. I said, no, it's not this, because we already have it. It's from different substation. Huh. Or maybe that's this. I said, no, we have it, this one, because it's already from different substation supply, because I have it on the list everywhere, and I'm missing 2 things. And they're like, oh, we have to find it. And sometimes it's very often that I find out we actually remove the covers, and you find out there is no cable, but things are energized. And I can understand it, because people hesitate to switch it off. Because I said, just switch it off, yeah? And they're like, later. So I can understand this hesitation, but it's like, okay. But there are a lot of things, small things like this, which are making the calculation much harder to do. So just to keep this in mind, yeah, that you need to have really the as it is, not as someone thinks it is, as it is. That's why the site visit is important. You don't always have to do it, but because if you do the greenfield project like the new one, there's nowhere to go, yeah. So we work on the design and documentation, but If this is existing factory, existing site, and people say, no, we have everything, 90% of time, 95% of time, they don't have anything. Because they are sending me some random things like breaker is NSX 160. And I said, yes, and the settings, and the rating of the breaker. And they start saying, what settings? And they said, oh, it's 160 amp. I said, yes, and there is something below which is adjusting the settings for the tripping. And then we know we have to go to site. Again, we have to code back and so on. So we have to go for a few days to collect the data. But that's one of the most important part, because this plus modeling is probably like 60-70% of work. The calculation, when you use software, is like really calculation that is just happening. You have to prepare a lot of things for it. But at the end, it's like clicking, yeah? And you have to work later. That this part that I show you with the recommendation is also second part, which is most or the hardest one, because you have to know what you are doing. Because when you start adjusting things, it's not just randomly adjusting things; it's just adjusting so it works, yeah. And it will not kill anyone later, or not let's say kill the installation or cables and so on. So adjusting things, that's why pretty much you will not see it often, yeah. So making the improvements, recommendations, and everything else is one of those second hard steps. Just to get to the point, this is what you have. It's one thing, yeah. If it's good outcome, that's good. But just to get to this point, later you're supposed to do some improvements. But improvements are, the calculation is just entering point to find out what you have to do. Because you have I can give you a lot of examples, but you can have like this generator case that where you have an incoming side of the generator, very high energy. There's nothing you can do really with this. So you have to think on the other layer on the procedures maybe, yeah? And things like this. Maybe on the PPE, but there are a lot of other things which are not calculation related. And this is the whole system. Okay, stop, because I will just keep going like this. If you want to ask, we have lunch. You can ask later.
Okay, so we're breaking for lunch, but today it's only 35 minutes. And I know I'm stealing approximately 20 minutes to half hour of your lunch.